So we are giving this particular proof in cell kinetics and fermenter design. When you're giving your growth yield to be C subscript x minus Cx naught over negative into Cs minus Cs naught. So you want to show that this particular integral over here results in this particular solution over here. So we are going to begin right away. So the first thing is to write this integral. So in terms of the main integration variable. Okay, so we are going to look for a way to replace this C of S here with we are going to look for a way to write it in terms of Cx naught and Cx and y of s. So the first thing is you're going to, from this formula, yx of s, that's our growth here, we are going to make C of s the subject over negative Cs minus Cs naught. So making the subject of the formula, you agree with me that okay, I can just see yx of s then into Cs minus Cs naught, then is equal to Cx naught minus Cx. Okay, so this negative sign, I used it to divide the terms in the numerator of this particular position. So when you open the brackets, we're going to have yx of s Cs minus yx of s Cs naught is equal to Cx naught minus Cx. Then you have yx of s Cs is equal to yx of s Cs naught plus Cx naught minus Cx. So I will come back to this equation. Let me reference it as equation 1 for instance. So let's keep going. Now if we make Cs the subject of the formula, we're going to have it as 1 over yx of s into yx of s and Cs naught plus Cx naught minus Cx. So this is our equation 2. So let's go back to the integral. So in going back to the integral, we have the integral to be sorry, let me change the ink, something else now. Let's use black for a while. Alright, so we have the integral to be integral from C, is this a Cx naught? Yeah, Cx naught to Cx. So we have Ks plus Cs all over mu max Cs Cx dCx, right? And this integral is somehow equal to, we have our T naught to T dt. Okay, so we're going to substitute the value, sorry about that. We're going to substitute the value of Cs into this integral. So in substituting the value of Cs into this integral, sub Cs into integral. In substituting Cs into the integral, you have integral from Cx naught to Cx. So we have ks plus cs. Sorry about that. Ks plus, instead of cs, now you can now replace it with 1 over yx of s into yx s, then cs naught plus cx naught minus cx, like this, and all over we have mu max, then we have cs. I still made the same mistake. So instead of it to have cx, you can have 1 all over yx of s into yx of s cs naught plus cx naught minus cx. Then you now have cx outside the bracket. So this is dcx, and this is equal to c naught to c dt, like this. So all right, it's getting complicated, but let's go together. So first of all, I'll extract the constants from this integral. So in extracting the constants, which is u max and 1 all over y x of s, it becomes yx of s over u max, integral from cx naught to cx, and you now have ks plus 1 over y x of s into yx of s cs naught plus cx naught minus cx, and all over you have yx of s, then cs naught plus cx naught minus cx, then cx dcx is equal to integral from t naught to t dt. So we are now going to consider the this particular term inside this place. We are going to consider this term. I will split it into partial fractions. So consider ks plus 1 over yx of s into yx of s, and cs naught plus cx naught minus cx over we have x of s cs naught plus cx naught minus cx, like this. Then we have cx. So this is equivalent to a partial fraction, c a over we have yx of s, then cs naught plus cx naught minus cx, then plus b over cx. So we are going to find the values of a and b using our knowledge of partial fractions. So to find the value of a and b using our knowledge of partial fractions, what are those going to be? So I'm going to use cover-up method. So using cover-up method, a is the limiting value as c of x tends to. So look at this particular linear factor in terms of c of x under a. So this particular linear factor, so you're going to ask yourself, what are you going to put into c of x to make this particular linear factor 0? And that is definitely yx of s, then cs naught plus cx naught. So this is what we are going to put in. So on this particular right hand side, you're now going to cover up this linear factor. So this linear factor will no more exist on, sorry, the left hand side. Rather, I said right hand side. So we'll have k of s plus 1 over y x of s and y x of s cs naught plus cx naught minus cx of cx, like this. So by the time we solve this partial fraction, when we solve this partial fraction, what are we going to get? We'll get k of s plus 1 all over y x of s. And we'll now have, so this particular one, all you just need to do is to replace this particular one with this particular term. Anywhere you see x, put anywhere you see cx, put y x of s and cx naught plus cx naught. Okay, so you now get y x of s cs naught plus cx naught minus the same thing, y x of s cs naught plus cx naught, and all over y x of s cs sorry plus cx naught, right, like that. So you can discover that this bracket is cancelling out, so we're just left with k s over y x of s cs naught plus cx naught, so as the value of our a. So let's go ahead and find b. So b, in the same vein, will be limiting value as c of x tends to what? So what's linear factor? What is the value that you have to put into the linear factor here to make it 0? And obviously is actually 0. So we have 0. Then when you now get back to this place, sorry, when you get back to the left hand side, we having our k of s plus 1 all over y x of s into y x of s and cs naught plus cx naught minus cx all over, then the other variable that we need to cover on this particular left hand side is this particular one, c of x. So when we cover it, we'll be left with only this particular one, only this particular linear factor, which in our case is y x of s c s naught plus c x naught. Sorry, let me get it well. Cx naught then minus cx minus cx. So by the time we substitute cx equal to 0, the value that we are going to get for b is ks plus 1 over y x of s, and you have y x of s cs naught plus cx naught all over y x of s cs naught plus cx naught. So now that we've found a and b, we're now going to go back to our integral. So moving back to the integral, so let's just scroll up and see what we had. for the integral. Sorry, this may take time. Alright, so we're now going to replace everything on this particular stuff with its partial fraction equivalents. Is that okay? Replace everything here with the partial fraction equivalents, and when you do that, this is what you get. So we're now going to get y x of s over mu integral from cx naught to cx. So for a, you got ks all over, what do we get for a? Remember, I got this, so let me just bring it down so that you can be seeing. Ks all over y x s cs naught plus cx naught. So this is a all over, the linear factor under a is y x of s cs naught plus cx naught minus cx, then plus v is now this whole stuff plus 1 over y k of s into x of s, not k of s, x of s cs naught plus cx naught, like this, and all over y x of s cs naught plus cx naught, then all over cx, like this. So we are integrating with respect to what? And this is integral from t naught to t dt. So we keep going. I have to make my handwriting much more finer. So this is mu max. So we have y x of s over mu max. So we now have integral cx naught cx. So we have ks over y x of s cs naught plus cx naught. So we have y x of s cs naught plus cx naught minus cx, now plus k of s plus 1 over y x of s into y x of s naught plus x naught. Cx naught, sorry. So now I want you to take note this whole term here is is a constant, so it can be taken out of the integral sign, and this whole here is a constant. You can also take it out of the integral sign. Alright, so if we solve this integral very well, this is what we are going to get. We're going to get y x of s over mu max. We now have ks over y x s c s naught plus c x naught. Right? So this whole thing is outside this integral. We have x naught cx. So we have 1 over this integral is y x s cs naught plus cx naught minus cx. So let me just put it cx here. Okay, I'm opening the integral at once, plus it will still be y x of s over mu max. Then we will have this whole constant here, which is k s plus 1 over y x of s into y x s and cs naught plus cx naught over y x of s, and we now have cs naught plus cx naught like this, and our integral is from cx naught to cx, and the integral in this case is 1 over cx dcx, and everything will be equal to c naught to t dt. Exactly. So when you organize it like this, the next thing that you're going to do is we're going to integrate now. I'm going to integrate this. I'm going to integrate this. Exactly. So we'll have y x s over mu max. We now have ks over y x s cs naught plus cx naught. When we carry out this integration on this side, take note of this negative variable here. So if you want to integrate this correctly, you have to differentiate this particular parameter negative cx with respect to cx, and to give you -1. So I'm going to put a -1 outside the bracket here, -1. So after putting that -1, and I can now do something like this, cx naught cx -1 over like this. So the essence of putting this -1 here and here is because when all these are constants, these terms are all constants, and this particular one is a variable, and you want to integrate it, so you differentiate this term over here first, and it gives you this -1. Okay, so you have to like put something to cancel the effect of this -1 that you introduced, because -1 was not here originally. So since -1 was not here originally, we have to put another -1 to cancel the effect of this -1. Okay, so that -1 times -1 can give us 1 back to normal. I hope that's fairly understood. So there is a rule of integration, quotient rule of integration, that we're going to apply to get our answer. So Meanwhile, if we go ahead to integrate this one, we'll have yx of s over mu max, and we'll now have ks plus 1 over yx of s. Now have yx of s cs naught plus cx naught over yx of s cs naught plus cx naught. Like this. When we integrate this particular one, we're going to get ln cx, and we're going to take it from cx naught to what? Cx. Like this. That's our definite integral. And remember, everything is equal to the integral from t naught to t dt. So let's keep going. So this particular place now gives me yx of s over mu max. Then we now have, sorry, let me put the minus sign. We now have ks over yx of s cs naught plus cx naught, like this. So when you integrate this whole term, you're going to get ln yx of s cs naught plus cx naught minus cx. So this ln is taken from cx naught to cx. Is that okay? Then plus you have yx of s mu max ks plus 1 over yx of s into yx of s cs naught plus cx naught over yx of s cs naught plus cx naught, like this. So if you evaluate this particular one, let me show you what you get. Let me just reduce it a little. If we evaluate this one like this, we are going to get it to be equal to, sorry, not equal to, I want to evaluate this, so it will be ln cx minus ln cx naught. Okay, and everything is equal to t, evaluating the integral from t naught to t, definite integral. So let's keep going. So if we keep on going, we now have minus yx of s or mu max, and we now have ks over yx of s cs naught plus cx naught. So evaluating this one, we're going to get ln follow me, yx of s and cs naught plus cx naught, right, minus cx, like this, and minus ln yx of s, I now have cs naught, right with me, then plus cx naught minus cx naught. Okay, then this plus, let me just bring it down here, then plus yx s mu max, and into ks plus 1 over yx of s then y x s c s naught plus c x naught, like this, over y x s c s naught plus c x naught. Okay, so applying your law of logarithms to this particular place, you agree with me that this will become natural logarithm of cx over cx naught. So everything will now be equal to, so if you apply the definite integral, this will be t minus t naught. So let me just leave this one like this, t minus t naught. So if we now label on this particular part, this is what we are going to get. We'll get minus y x s over mu max, then we have k s over y x s c s naught plus c x naught. Then if we evaluate this particular place, because this is where the challenge is, but don't worry, we'll soon overcome that challenge. We'll have ln of natural logarithm of y x s c s naught plus c x naught minus c x, and minus natural logarithm of y x s c s naught, then cx naught, right? So these two terms has cancelled out, so they become 0. All right, so it becomes 0. So on this part, we now have it reduced like this. So we now have plus this whole term yx of s over mu max, then ks plus what do you have, 1 over y x s into y x s c s naught plus c x naught, and all over y x s c s naught plus c x naught. Then we have natural logarithm of cx over cx naught equal to t minus t naught. So at this point, to make things simpler and more shorter for me on the left hand side, we can multiply LHS through by mu max. Or is it multiply only the left hand side? Sorry, we're multiplying everything, left hand side and right hand side, by mu max. So if you multiply the left hand side and the right hand side by mu max is going to cancel out. We're going to cancel out on the left hand side, and it's going to appear here on the right hand side. So in as much as we are doing that multiplication, we're also going to be doing some little simplification. Now this minus sign this minus sign, I'm going to apply it inside this particular bracket, and this minus sign can reverse the position of this term and this term. So watch how we are going to do that carefully. We will have y x of s, then you have ks over y x of s cs naught plus cx naught, like this. Then remember, mu max is gone because we've multiplied through. Now that minus sign is going to come inside this particular logarithmic bracket. It's going to make the expression ln y x s cs naught, like this, minus ln y x s cs naught plus plus cx naught minus cx, like this, All right, then plus, let me try to squeeze the whole of this one here. So in squeezing this particular one, we'll have y x s and k s plus 1 over y x s into y x s c s naught plus c x naught, like this, and y x s c s naught plus c x naught. So don't forget the ln cx over cx naught on this place, which will give me mu max into t minus t naught. So something like this is what you have. So once you're done with writing it in this way, now it's going to be actually a long hell of proving here. So we are going to apply the law of logarithms on this place. So let's see how it reduces. So we have this multiplied by this is y x of s, then ks over y x s cs naught plus cx naught. All right, so applying the law of logarithms on this place, you now have a ratio which is y x of s s and cs naught over y x of s cs naught plus cx naught minus what, cx, like this. So you have this particular ratio on your logarithmic part, then you now have plus. Now let's focus on this bracket and let's do some reductions here. So assuming that you use this particular one to open the bracket, use this particular term here to open this bracket while simultaneously dividing this term and this term, okay, by this denominator. Watch what is going to happen. Just follow me carefully. So yx of s times ks gives me y x of s, then you have ks, then I'll now divide by this term, divided by y x of s cs there's a naught here, cx naught plus cx naught, like this. So I've done for this particular term. Then y x of s multiplied by its reciprocal is going to give me what, 1, right? So plus 1, then this divided by this is going to cancel out because they are similar. So the whole of this bracket reduces to this term. So you now have your ln cx over cx naught, and this is equal to mu max t minus t naught. Is that okay? Now the next thing you're going to do is you're now going to see something that I told you. Now you see this particular expression, so let's scroll up. We have yx of s, then cx naught, then yx of x cx naught plus cx naught minus cx. So I want you to recall. You can pause the video and go back to the place where I referenced equation 1. Recall that yx of s cs naught plus cx naught minus cx. Recall that this term from equation 1 is equal to yx of s, then cs. Okay, so you're going to replace the whole of this particular stuff with this guy over here on this particular side. So when you replace it, this is what we'll get. and we replace it, we are going to get y x of s, then ks over y x of s cs naught plus cx naught ln, we'll now have y x of s cs naught over y x of s cs, okay, then plus y x of s ks over y x of s cs naught plus cx naught, everything here plus 1, and now have a ln cx over cx naught. So this is equal to mu max into t minus t naught. So having written it like this, you can now discover that these two terms can cancel out. Alright, and when they cancel out, you can just do some rearrangements, right? First of all, mu max into t minus t naught is equal to, so let me start with this term. We'll have y x of s ks over cx naught plus y x of s cs naught and plus 1 ln cx over cx naught, then plus y x s ks over cx naught plus y x s cs naught, like this, then ln cs naught over cs. So this is the end of what we are trying to drive at, and I believe if you followed up to this point, you should be able to navigate with the solutions. However, if there is any problem, at all, or if there's still any confusion at all, you can leave a comment and just ask me a question and comment. How did I get this? How did I get that? And I'll be glad to explain more and more and more for you till you're satisfied. So don't forget to like, subscribe, hit the notification buttons. This channel is basically for solving engineering mathematics, truths, derivations, derivatives, differential equations, partial differential equations, and basically explaining anything that you want me to explain, so I could just explain something for you in field cutting across engineering mathematics. Okay, so share this channel, share information about this channel to your friends. I hope it's beneficial to them in the long run. Alright, take care of yourself. See you next time.